Okay. Can everybody hear me?
Yes, we can hear you.
Okay. So, the lecture of today, we finish the chapter related to dynamics of articulated robots. And last lecture, we were describing the method of Newton-Euler to derive as an alternative method to, with respect to the Lagrangian one, the dynamic model of a generic robot. We said that Newton-Euler can be better used for inverse dynamics or computed torque to compute the pattern of torque contributions to give to the actuator to achieve a certain motion because of its linear complexity in the number of joints. But we saw also that we can use that for direct dynamics. Computation is not that efficient, but in case we want to use for direct dynamics, we need to first compute, given the state of the robot, position and velocity of the joints, the bias terms that are nothing more than the Coriolis centrifugal plus gravity term together. And for that, we call the function of recursive Newton-Euler setting 0 for the accelerations. And then we need the inertia matrix. And for this, we need to call n times the recursive Newton-Euler for one for each column. So we have quadratic convexity. And then we can, as a last step, compute the acceleration using the inverting the formula of the dynamic model we have, isolating the accelerations. And you can always isolate acceleration because the inertia matrix is a positive definite matrix. So it always exists an inverse. Then we have as input the vector of input torques, for example, coming from the controller, and we get the output as output the vector of joint acceleration. And to get the we need to update then the states. From the acceleration, we need to compute the velocities. From the velocity, we need to compute the position. And to do so, we need to employ an integration method that could be, in this case, the most adopted one, because we are not dealing with a stiff differential equation in case of a manipulator in free motion. We can use Runge-Kutta-4 or forward Euler. We can see briefly the forward Euler description. And integrating the acceleration, we get we update the vector of joint velocities and positions for the next step, and then we iterate. This is our simulation block that we will implement in the final lab of this course. And first, let's describe what is forward or explicit Euler integration method. We want to integrate acceleration into position and velocities. And the assumption of this explicit Euler method is that we do a Taylor expansion of the of the function we want to integrate, and we stop the approximate only, we stop the Taylor expansion at the first order. So it's a first order method. And the assumption is that the acceleration is constant during the time step, while in reality it's not. And this means that even though the acceleration will change during the time constant, during the time of the integration step, we assume that it's constant for the whole step. And doing so, we can derive the velocity at the next step, which is k plus 1, which is q dot of t plus delta t, where delta t is the integration step, is equal to the previous velocity at the previous step plus dt q dot the acceleration at this time step. For the position, do something similar. Oh. We take the previous position at the previous step, and we, in essence, integrate the velocity. And this is forward Euler approach. However, since we have a second order system, we can improve this and directly integrate the position directly from the acceleration. So if we think about doing a double integration of acceleration, we have q dot double integration on dt. We get the linear term q dot t plus the constant of integration that relates the initial velocity in dt, and then we get this expression once we solve also the second implicit integration. And therefore, we can improve the previous, sorry, I think we call it, yeah, dt non delta t. The velocity part will remain the same, while the position will have this direct dependency, sorry, on the acceleration. So is the position previous step plus velocity times dt plus t squared, sorry, dt squared half q dot on the previous step. And this is improved forward or explicit is the same Euler. That is better for our specific case because we have a second order system. In general, we will use the other formula if you don't know the specificity of your system. So we are integrating both velocities and positions because these are our state variables. If we have a first order system, we would all integrate for example, only positions or depending on the dynamics, on the order of the dynamics. And why forward Euler it's favorable because its main pro is that it's easy to understand and implement. You see, the formula is very easy. It's computationally cheap for one single step. And the cons is that it's low accuracy because it's a first order integration step. So we get an approximation of the first order to the integration error. Then what happens if we want to have higher accuracy? In this case, we need to use higher order method, like a Runja-Kutta 4, for example. But this is not really necessary for a manipulator in free motion. However, if we select the delta t too large, we get a large integration error. And also, this error is due to the fact that we assume that the acceleration is constant during the integration step, while in reality, it varies because it depends both on the inertia matrix, that is position dependent, and on the Coriolis centrifugal terms that are both position and velocity dependent. So Q and Q dot, in reality, they do change during the integration step. And therefore, if we take the integration step too big, we can start to have that this approximation is no longer valid. While if we take it small, we can assume that the inertia matrix and the Coriolis term don't change so much, and so that the acceleration is approximately constant through the whole integration step. However, this approach doesn't work for stiff differential equations. For example, when you have discontinuities, you remember the Coulomb friction, or you have different time constant. You remember the electrical motor with the fast electrical dynamics and the slow mechanical dynamics. However, as I said, our manipulator in free motion is not a stiff dynamical system, so we can use explicit Euler with quite small time step from 1 to 5 milliseconds. While in the case of an electrical motor, it wouldn't work, and it would be it would be unstable and inaccurate. The good thing of the remember space equation of our electrical motor is that it's linear, so we could use an exponential matrix rather than a Newton-Euler method to integrate it. But in this case, since it is a nonlinear system, our manipulator dynamics, we cannot use the exponential matrix. There are also implicit methods like implicit Euler, but they need to require to solve a system of nonlinear equations, so they are more complex to implement, but they are more stable. And as this, the example that makes differential equation stiff, we have the Coulomb friction. In this case, what can help is to reduce the dt or use a better integration method. But if we reduce the dt, then the simulation time increases because it takes more time to do more iteration. So this part is finished, I would say. Do you have any question? Excuse me. Yes. Can you do another example about stiff differential equations? Yeah. Another example is, for example, we will see in the next lecture, is whenever you have the robot which is in contact with a stiff environment that is represented by a spring with a K very large. So if you think about if you press against the spring with a motion, so the manipulator itself will have some dynamics, so cannot move faster than some rate, let's say, as some natural frequency, and the actuator capabilities and everything is making such that the motion cannot be larger than something. But if you have a very stiff spring, you have the spring equation is K over delta X, and this could be seen as K integral of X dot, where this is the effector velocity, let's say V dot, we call it, or V. So if you have a very high stiffness, it means that if we approach the contact with very high speed, you will get a very high derivative. The force will build up very fast with respect to time. While if we have a compliant environment, the force will build up as integral or velocity slower. So you can understand that this is correspond to the very fast dynamics, while way faster than the manipulator dynamics. So you need to be able to since you have both dynamics whenever you are simulating this system, because you have the dynamics of the manipulator and the dynamics of this spring that represent the environment, your differential equation are badly conditioned when you need to solve, because you will have some variables that change very quickly, and you will have some other variables that change slowly, more slowly. And this is an example of stiff differential equation situation.
Thank you.
Welcome. Okay. Can you see everything in the slides?
Yes, yeah.
Okay. So in this lecture, I would like to extend the dynamics of our manipulator to take into account the fact that this manipulator is no longer in free motion, but could enter in contact with the environment. And this environment interaction will make appear a contact force. And sorry, take the pen. Okay. And so the focus of this lecture is on the fact that there are forces exchanged with the environment, and what will be the dynamics, the motion of the robot, which means the dynamics, when the manipulator is in contact. So we have till now described the case of free motion. We didn't talk much. We said that there is a mapping between Cartesian forces and joint torques. we saw that they enter in the Lagrangian on the right-hand side as non-conservative forces. We have position encoders to read the sensor to read the joint position, but now we might have also a force sensor at the end effector, and we are considering the situation when the robot is in contact with the environment. And we want to describe the dynamics whenever the robot is in contact. So first, imagine we have an infinitely stiff environment and a 2D case where the robot is a simple mass subject to two Cartesian forces. One is Fx and one is Fy on the horizontal and vertical direction, respectively. Then we see that we, in case we can get or not in contact with the environment, we have different situation. And the first case I cannot write. Okay. The first case in when the position of this mass is far away from the position of the environment. The position of the environment is represented by this XC position that represents the position of the wall. So in case our robot is far away from the environment, the external force coming from the environment is 0. Then we can have a second case in which the robot is in contact with the environment and we can have that applies 0 force and remains in contact. And if apply a positive force, we'll get try to enter into the surface, but since the wall is very stiff, the environment is very stiff, it will not move. And in essence, we get let's assume that we approach the environment with 0 speed and velocity, or very low one. Then if we write the equations of this simple model, we have mx dot dot, the horizontal balance of forces, Newton law, fx plus fx, and then we have the vertical dynamics, which is fy. So in the situation in which we applying a force fx and we have a 0 acceleration, we have an algebraic force relationship between fx and fx, because this goes to 0, and we get in essence fx equal to minus fx. Okay, let's assume there is no friction at the contact, so whenever this is in contact, it can freely move on the other direction following the other equation. So you can freely slide along the contact if you don't have friction. So the external force of, coming from the environment will be opposite to the commanded force from the robot. But okay, what happens if we approach the environment with the velocity which is non-zero? we have two situations. We can have, for example, an elastic impact. Let's say we approach the surface with non-zero velocity along the normal to the surface, and we hit the surface. And if we have an elastic impact, it means that the velocity right before the impact, which is x dot or p dot x dot minus, it's let's say it is positive, and whenever the impact occurred, if we have an elastic impact, we have that the sign of the velocity is reversed and is opposite to the velocity before the impact. So there is no energy loss. All the momentum, linear momentum, is conserved. It's just flipped. And with a full return of energy. But if there is so in this case, it bounces back without losing energy. But in the case of inelastic impact, the velocity after impact, it's yes opposite with respect to the velocity before the impact, which is x dot minus, but it's a fraction of that. So we have energy loss. Still positive and negative. And you have a full perfect inelastic impact, perfect inelastic condition if this scaling is 0. So the velocity after the impact will be 0. And this means that all the kinetic energy or the of the system in the impact is lost. And in case of rigid contacts, we assume this is the case for simplifying our modeling stage. So in general, yeah, let's not complicate this. The other possibility instead is to have a soft environment. And we typically model this soft environment, softness of the environment by the presence of a spring. This is like a wall suspended by a spring with whom the robot entering contact, and the spring, whenever the robot enters in contact, will be deflected. There will be an elastic reaction force that is generated proportional to what? Proportional to the deformation, which is the position. Let's see. Deformation, the penetration of the deformation of the spring, which is xc, which is the position of the spring that is not compressed at all, the free uncompressed spring, and the position of the robot. So when this becomes negative, it will react with a force. Otherwise, the force will be 0. So we have a unilaterality here condition. In this case, we don't care if the velocity with whom we approach the surface is 0 or not. It could even be non-zero, and the momentum will be absorbed by the potential energy of the spring. If the speed is too high, it means that the effects, the reaction force from the spring, can become very high and can reverse the motion very quickly. And in that case, we can have the robot that is bouncing back from the wall. If the stiffness becomes infinite, then the compliant environment is equivalent to a rigid environment. And we can also add a damping term that represents the damping of the environment in parallel with the spring. That will be proportional to the rate of penetration. Create a force that is proportional to the rate of penetration of the wall. Okay. Now let's see two ways of modeling this dynamic contact that are consistent with these two simple examples. And the first one, it consider rigid contact assumption, and it's constraint robot dynamics. So to compute the constraint robot dynamics, we start with our dynamic model, unconstrained, and we define a task output function R that represent our task variable that are in contact or that are meant to be constrained. So let's think about not only a contact as we see now, but as a constraint on the motion, for example, of the end effector. In fact, so these are the task variables that interact with the environment, and we might need to be able to use this method to define a geometric constraint on these task variables that represent the way we want to constrain the end effector. And the limitation of this approach, we will see, is that the contact is bilateral. So think about you are handling a bar and you can both pull and push against the bar, or like in an example, a slider crank mechanism that it's moving, and you can have both pulling force and pushing force. While in case you're pushing on the wall, you have only unilateral constraint. So this is, for example, if you want to design a robot that needs to move in a rail, needs to perform some operation, constrained operation, or for example, moving on a circle. So in this case, the constraint is circular. And we see that we keep our formulation as before. In the case of free motion, we are not changing the number of generalized coordinates, but we filter out from the dynamics, or we better say we project the dynamics in a way that takes account of the constraint. Takes into account the constraints. So in the case of the end effector in contact, what could be, no, sorry, not in contact, on the rail, because is a bilateral contact. And let's say we want to keep the end effector position on the rail and still. So we want to clamp it there. And this means we want the end effector to be constant, position, for example, to be constant. And if we write this as we described before, something that is constraint geometric function of R, we get a constraint on the task space. While if we use the forward kinematics and we know that this is our task function is function of Q, we can write this constraint at the joint level and we call it h of Q equal to 0. Okay, it's a function of Q. And this is a constraint in joint space. So we map the constraint from the vector space to the joint space, and we can change our Lagrangian, for example, for the computation of our dynamic model, to incorporate an additional term that is a linear function composed by a multiplier, lambda, that we will see is the contact force, which is an m-dimensional vector, same of the task function, multiplying the function, constraint function h of Q. And so lambda will be treated as an additional generalized coordinate, and is the force, the constraint force that arises when the constraint h are violated, and is also called Lagrange multiplier. So now we have a Lagrangian model to derive that has n generalized coordinate q and m lambdas. And I won't do the derivation here, but it can be proved if we do the same derivation with the Euler-Lagrange equations, that the model that is obtained in this case is the following one. And this is the constraint dynamics model of a robot that is satisfying the constraints h of Q equal to 0. So whenever you have a contact force or a constraint force, in this case of the robot to stay on the rail, you implicitly are also considering that there is a kinematic geometric constraint h of Q. Now for our example, again not in contact on the rail, because a bilateral contact, we have h of Q equal to 0 0, and this is this geometric constraint of Q equal to 0 is called holonomic constraint. And holonomic means that it can be obtained by the integration of the differential version of this constraint. What is the differential version? We do h dot equal to 0, which means doing the time derivative of this. If you do the time derivative of the r, we get the Jacobian times q dot, because we have r dot. And if you do the time derivative of a constant function, we get 0. So this is the constraint at the differential level. And the second thing we need is this partial derivative, and is, oh, this is only dependency on Q, so we can put a differential dr dq minus dr0 dq r0. This is constant, no dependency on the thing. Therefore, yes, this is just the Jacobian of the end effector on the rail. In our example. The point that we would like to put on the rail could be another point, could be one pin in the middle of the link. In that case, we want to use the end effector of the pin, position of a pin in the middle of the link and not the one of the end effector. So this is generic. In this case, the dynamic model simplifies explicitly the previous one wherever we have the the forces to keep the constraint, and we have the constraint of having the end effector in a constant position. Okay. Now, so this is modeling this example. We can think about to eliminate the lambda, the constraint forces from the dynamics. And to do so, we can differentiate twice the h constraint with respect to time. So h equal to 0 is this. And if we differentiate one with respect to time, we saw that we get jq q dot equal to 0. And if we differentiate another time with respect to time, we get jq q dot plus j dot q of function of q dot. Okay. Then we can isolate accelerations from the from our model and plug this acceleration into this. Okay. So we first isolate the acceleration from the model. Minus release, minus gravity, plus j transpose lambda. Now I won't put the subscript anymore, just to don't have it in notation. And we replace in free. So jq dot becomes jm minus 1 u minus c minus g plus j transpose lambda plus the other term here, which is j dot q dot. Now you can see that the lambda appears multiplied by these two terms, so we can explicitly express this. And we group the other ones here. And then we can compute the lambda, inverting this. And this, we assume that J is full rank, so it's always invertible. And we have what? See. We have the opposite sign, so we have C plus G minus U minus and minus 1 transpose minus 1 J dot Q dot. And this is the expression that allows us to compute these constraint forces that are needed to fulfill to respect the constraint. In this case, to don't move the end effector. We call this lambda C or lambda A, lambda. And this we call H, the famous bias term. Sorry, only C plus G. Therefore, we can write this way. And we see what? That the contact force depends both on the state, also on the mass depends on the state, the Jacobian depends on the position state, but also on the torques. So in rigid contact, we see whatever we saw in the simple example, that the external force will depend on Fx, on the commanded force. In this case, will depend on the commanded torques. And in rigid contact, you can estimate contact forces or constraint forces as a function of state Q dot and input torque U. Okay. Now, to make this lambda disappear from the equation, we replace it back. So first, let's define what lambda C is. This is the robot inertia, the joint space inertia, that is reflected at the end effector. Remember that whenever we were reflecting the motor rotor inertia of our electrical motor to the load side after the gearbox, we are multiplying this by squared of the gearbox ratio. This is the same thing. We have a robot inertia represented by the joint space inertia M, and we want to see what is the inertia at the end effector seen from an observer, that felt by an observer that is touching the end effector. Okay, and this mapping, of course, will depend on the Jacobian and as this expression. So what we said before, when the robot is in contact and we apply an input torque, the resulting motion might be inconsistent with the constraint that we set, for example, keeping the end effector fixed on the rail, and therefore a reaction force will be generated to make this motion comply with the constraint. And we can see that if we replace the expression of lambda back in the dynamic equation, we get the constraint consistent dynamics. So we replace back lambda in here. Okay. And then if we explicit all the terms, we can see that something very cool happens. We replace the expression of lambda capital, which is this one. J minus 1, J transpose, minus 1, J M minus 1, U. Now, don't be afraid. This seems ugly, but it's not that much. First, let's observe what is the shape of J transpose. We are talking, we have usually J is a fat matrix, so J transpose will be skinny. If we do the pseudo inverse, it will be a fat matrix. So let's observe what will be the pseudo inverse of a fat matrix. I recall you the expression here. And remember also that we can put a weighting matrix in this pseudo inverse, getting a generalized pseudo inverse, just putting the W matrix in this way. And then if we compute the pseudo inverse of J transpose, we apply this rule, let's say. So we take the transpose of J transpose, which is J. We take the J transpose as is, do the inversion, and the transpose of J transpose, that again is J. And if we put a weighting matrix, we put it here. And now you can have a look here. And this is nothing else that J transpose pseudo inverse with a weighting matrix M minus 1, the inverse of the inertia matrix. And this is called dynamically consistent pseudo inverse. It was discovered from Osama Khatib in Stanford University, one of the guru of robotics in the 80s. But apart from the pseudo inverse, we see that the U variable appears as an identity matrix and as something J transpose times J transpose pseudo inverse. And the same happens for the H. Here is with the identity, and here is with J transpose pseudo inverse. So we can collect this, and you will see we rewrite whatever we said. We collect the H, and we have the identity minus J transpose pseudo inverse. I don't put the weighting here just to don't have it in notation, plus the term of j dot q dot, and again we have the same thing for the torque. And what is this matrix? This is the new space projector at the force level. So it's the new space projector matrix that filters out all the torques that are not satisfying the constraints. So that produce some force at the end effector. That would violate the constraint. So this is the final expression of the, I replace lambda here, of the constraint dynamics. And this is the constraint consistent joint space dynamics. So it's the dynamics that if you compute acceleration from this equation, you will get acceleration that are consistent with the fact that the point should stay on the rail fixed. So if you have a null space motion, you will compute acceleration that are satisfying this condition. And if we replace again back j dot q dot equal to from free jq dot dot minus jq dot dot, we get something that becomes very simple. We collect the M matrix. So we have an identity here. And from this other term, we collect the M matrix. So we get this Jm minus 1 because M was not present here. And we have collected, sorry, mq dot dot, not only the M matrix, plus nh equal to nu. And this is, again, nothing else that the J transpose pseudo inverse, so this is n. Sorry, this is n. So in essence, if we collect, we are just projecting all the joint space dynamics with this matrix n. Okay. And this is equivalent. So doing this, the previous derivation is equivalent to projecting the dynamics through this null space projector. And what is this null space projector? Is a linear operator that maps the dynamics into a lower dimensional space where the constraints are satisfied. And therefore, the dynamics becomes independent from the contact forces. because this matrix filters out everything that will not satisfy the constraints. In fact, if we consider how this M is done, it's, so these are the contact forces, these are the torques, okay? And we saw that with J transpose, we can get from the contact force space or a constraint task space to the joint space, while with J transpose pseudo inverse, we go back to the task space. So in essence, this null space projector corresponds to torque that projects our torques into a space where there are torques, a subspace where there are torques that do not produce any force at the end effector. So if you have, for example, these constraint forces that are mapped into torque through Jacobian transpose, so you are here in the row space, and you multiply by the null space projector, you see that you get 0. And this is why, that's why if you have this multiplied by that, disappears and remains only the torques. So this is also useful, for example, if you want to do inverse dynamics and you want to, this time we don't have anymore the acceleration that is both dependent on forces and torques, but we have acceleration it's only dependent on torques. So we can compute a one-to-one relationship in the case you want to use this approach for inverse dynamics between the acceleration and the torques. But what is the problem of, so let's recap just to summarize and avoid confusion. We saw that at the velocity level, we have a null space projector for velocity that is done with the Jacobian. So we have the null space in the domain here, and we have the expression is taking the Jacobian pseudo inverse and doing I minus Jacobian pseudo inverse times Jacobian. And if we want to do like this, map back into joint velocity from end effector velocity, we see that using this null space projector, we can add some joint velocities that do not produce, are in the null space of J and don't produce any end effector motion. While these are the joint velocities that produce end effector motion. And the same thing for at the force level, instead of using J, we use J transpose, and the null space projector is the one we saw now. We do the inverse, the pseudo inverse of the Jacobian transpose pseudo inverse times the Jacobian transpose pseudo inverse, and this is exactly equivalent to whatever we just wrote before, because the pseudo inverse of a pseudo inverse is just the Jacobian transpose itself, and this is the Jacobian transpose pseudo inverse. So the shape of the null space projector formula is the same. It's just that we have this simplification, and in this case, the domain is are the torques, and we map the torques into the end effector with the Jacobian transpose pseudo inverse, and with Jacobian transpose we go back to from the effector to torques. So with Jacobian transpose F, we get into the row space. These are the torques that produce some force at the end effector, plus we can have a null space projection of forces that, sorry, torques that do not produce any force at the end effector. And this is exactly the idea of this constraint dynamics. So we will compute accelerations from forces that do not produce any motion at the end effector. So it will be consistent, like if you are not putting any force there. But this is so yeah. So we can do a more complex example. We, for example, consider a more complex constraint, not just staying still on the rail, but staying on a circle. So we, in this case, write this constraint in task space. This is a 2 degrees of freedom robot, and the geometric constraint function of R is X and Y component, is a circle of center X0 and Y0 and radius R. So this is the equation of a circle, and this is the expression of constraint equal to 0 in the task space. Then we have the expression of a forward kinematics for this robot. L1 C1 plus L2 C1 2 L1 S1 plus L2 S1 2. And then we want to rewrite this constraint in the joint space because we want to compute H. So we want to compute H of Q, which is just the task space constraint evaluated with the forward kinematics. And therefore, H of Q is our, we replace here and here. This is a two expression. Sorry, minus x0, everything squared. We replace the y component. And then we subtract the radius. We set this equal to 0, and this is the expression on h. And in the equation, we wanted to also have derivative of h with respect to q. Remember that before was just a Jacobian. In this case, it will be a little bit more complex because we need to differentiate. We have a composed function. We have the derivative of k with respect to r. And then we have a derivative of r with respect to q. Now, what is the derivative of k with respect to r? So this is, we know already, is the Jacobian. And derivative of k with respect to r, we look at this and we differentiate with respect to the x and y variable to simplify. So we get twice the argument because it's a quadratic argument. And we get 2y0 y minus y0 times the Jacobian. And if we replace the forward kinematics, we get the full expression. And of course, the R variable was disappear because it's a constant, and this should be multiplied by j. So in essence, we get a new kind of new Jacobian, JR, that has in the first part here some information on the contribution to the from the geometric constraint, which is the circle, and some other part which is our Jacobian. And with this R, we can compute the Jacobian of R derivative. We can compute the pseudo inverse, sorry, the transpose and the pseudo inverse. We can compute the new space projector. You can plug it in and get the constraint dynamics applying the previous formula. And obtain a motion that is consistent with this constraint. Now, what is the problem of this approach? Sorry, yeah, I would do a break now of 15 minutes. Then we continue with the next part. Yeah, let's come back at 7. Yeah, 10 minutes. Okay. Uh, let's start back. So the approach that I just presented has some limitations, and because think about the fact that why we did that. We did that because we want to ease the integration of the acceleration, because we have both torques and contact forces, and we wanted to get rid of the contact forces to do a simple integration of the acceleration. But this in a lower dimensional space where these contact forces are not present. But this doesn't mean that these contact forces do not exist at all. Actually, they are there, and they can be computed using the formula that we presented at the beginning of the lambda. Now, I need to be careful. See this formula, sorry. So the contact forces is a delay. Could be computed with this formula. And so in case we want to do inverse dynamics, this formula it's very nice, because given the motion, we compute the torque that are meant to be not violating the constraint, like keeping the end effector in some position. But this will assume that the end effector is already in satisfying the constraints at the beginning. So we just apply some torques that are okay. But in case we want to do forward dynamics, so we have the torques, whatever they are, and we want to compute the acceleration and integrate them to see the motion, it might happen that these torques that we provide, for example, from a controller, they are not for example, in case of unilateral constraints, they might ask to break the contact. So this approach works if the contact force or the constraint force can be whatever. Let's think about, we can pull and push on the geometric constraint. But if we are pushing against a wall, we are in contact with a wall, the wall will provide a contact force if you are pushing, but will provide zero contact force if you are pulling. So this approach is not really useful in this case. Additionally, if you have multiple contacts, you need to check all the combination of contacts, and you would have to remove the contact for which the contact force along the normal to the contact becomes negative, because in case of unilateral contacts, the force, the robot can only push but not pull. So this means you need to evaluate many combination of contacts, stacking the Jacobian of each contact. Let's think you are these two contact situation, you already have three combination, one in which both contacts are active and you compute the lambdas, one in which only first contact is active and you compute the lambda, and the other one when the second contact is active and you compute the lambda. And if sum of the lambda becomes negative in a normal direction, then it means that you are pulling, so you need to remove that contact assumption. This is not really doable for many contacts. So what people do usually, they cast all this as an optimization problem where they enforce unilaterality constraint, inequality constraints. So they ask for the force to be positive along the normal direction. Alternatively, you can use the other approach that is referring to the second example simple example that we did, that assumes that the world is not infinitely rigid, and this approach works easily with unilateral constraints. So if the world is not infinitely rigid, means that whenever the robot enters in contact with the environment, there is a small deformation, and we on the surface at the contact point, and that contact force that is generated is proportional to the deformation, as a spring and a damper. So, for example, if we have P0, the initial contact point where the robot initially enters contact with the environment, and P, the current position of a point in contact of a robot that is in contact, then using linear spring and damper, we can compute the contact force as in this way. We have Kc, which is the contact stiffness, position of the end effector. P0 is the position of the environment, P in position of the end effector, that in this case is inside, and you see that P0 minus P is a vector like this, and so we have a contact force coming out from the environment, plus minus, because the damping is proportional to the velocity, rate of change of the position of the end effector. And this is happening if n transpose, where n is the normal to the contact. So we project this vector along the n, and if this is positive, then it means that this is on this side. Otherwise, if it is on the other side, we'll get something negative, and in this case, we want to set the force to 0. And this is the models the unilaterality. That we couldn't deal with the previous case. So in previous case, since we were enforcing an inequality constraint, we need to have a bilaterality. Otherwise, we would have used inequalities constraints. But in this case, it's very simple. In Kc is contact stiffness, usually ranges depends, of course, on the material. The steel is more rigid than the wood. The wood is more rigid than the rubber, and usually it ranges from 100 to 10 to the power 6. And dc is the contact damping, and usually you set equal to square root of the stiffness. Note that now the contact force is no longer an unknown over dynamics, and it becomes a function of the state always in every case. And therefore, because we have an algebraic relationship here, And then we plug it in the previous equation that the algebraic equation that we compute. We plug it in the dynamic equation and we get the dynamics with compliant contact. And this is the way we will implement in our lab. Additionally, you can set different stiffness in different directions. For example, in the Z direction, we could have a stiffness and a damping, while in the X direction, another one. So you can model different material behaviors. You can even generalize away from the linear model of spring dampers using, for example, nonlinear springs that are, for example, stiffening springs, or springs that are not stiffening, like foam. I show an example in next video. It's a nonlinear spring. And in this case, in our simulator, you have the equation of rigid body dynamics, and you have the contact model that receives the states, compute the force, feed it back to the rigid body dynamics, and then with the control input, compute acceleration, we integrate acceleration, get the position and the velocity of the joints. So this is how the simulator is set up in this case. And here you can see some experiments we did with IQ, trotting on a foam, and we had to, in our simulation, implement this soft terrain simulation with the compliant contact. Unfortunately, the video is not really, it's a bit stuck. Well, to summarize, the compliant contacts, as you've seen, are easy to compute. They can have problems, as we said before, because the differential equation can become numerically stiff whenever the stiffness of a spring, of environmental spring, is high. And this means that we need small integration step to be integrated, and this leads to slow simulations. You can see the rigid model as an infinitely stiff compliant model. We have here the compliant model where we have penetration and force. So you move along this slope where along this line where the slope of the line is the stiffness itself, while the rigid infinitely stiff model, which is the rigid case, it's providing a force whenever there is no penetration, and zero force whenever the penetration gets positive, which means whenever the end effector gets out from the contact. And this is a very nasty thing, because we saw that in case of rigid contact, we can use the constraint dynamics to do inverse dynamics. It's good for control. It's not so good in case you want to simulate unilateral contact for the forward dynamics. But the rigid contact assumption is also nasty because it's not differentiable at this point. It's not smooth. So whenever you want to compute a gradient, you get a discontinuity in this point, and optimization methods that are based on the computation of the gradient have problems to work. So you need to do some approximation, smooth approximation of this behavior. Okay. If you have any question on this. Otherwise, we go to the very, very last topic of today, which is the last topic of the dynamics, and is a very, very, very superficial introduction on what are underactuation and the actuated robot. So first, I give you some motivation. We have the classical control techniques from robotics that are based on the idea of feedback that usually is used to override the dynamics of our machine instead of exploiting it. So we want to force a tracking of a trajectory. But there is a lot of waste of energy in that because these control systems are usually using high gain feedback and therefore a considerably high joint torque. And to cancel the natural dynamics of the machine and strictly follow a desired trajectory. While to achieve fast, efficient, and agile motion, we want to plan and control, use control methods and planning methods that exploit the natural dynamics, which means rather than trying to cancel it, as we will see in the next lectures on control, the inertial coupling, gravity, elasticity, we will think about using them, take into account them in a way that we can exploit them. And because underactuated systems are systems with less actuators than degrees of freedom, this is usually the way you can try to control these systems. You cannot do much better. Sometimes underactuation is intrinsic to the nature of a mechanism, and sometimes it's an intentional choice. For example, if you want to save cost and weight, you might decide to use less actuators than the needed ones and try to do the best that you can with the others. And this sense, a very famous example of an underactuated robot is the cart pole system. We have a cart that is moving, so we have an actuation input force at the cart position. I'll show you again. And we want to, we have a passive joint, rotational one, that we want to put it up, moving the cart. So the rotational joint, it's passive, and we have one actuation input, which is the force acting on the cart, and 2 degrees of freedom, which is the position, horizontal position of the cart and the angular position of the link, of rotational link, of rotational joint. And so a very simple example is to balance this pendulum around this unstable equilibrium using the forces on the cart. While another example of underactuation is the Acrobot, which is a two-link robotic arm acting located in a vertical plane, and it has an actuation only at the elbow, but no actuation on the shoulder. And if you look at that, again, we want to try to swing it up, and it's possible, exploiting the passive dynamics of the second link, or the first link. The dual of this is the Pendubot, which has an actuator not at the elbow, but the elbow is passive, but will have an actuation at the shoulder. But let's be more precise. We said that underactuation is having more degrees of freedom than number of actuators. In general, the underactuation is considered a global property of the system. So we refer to a system as underactuated if it's underactuated in all states and times, because sometimes, for example, we have situation whenever we are losing rank in a kinematic singularity, where we lose control, we lose actuation capability, or for example, we have joint limits. So in case a manipulator is hitting the joint limits, we don't say that we have an underactuated robot, but only whenever, always, all the time, we have less actuators than degrees of freedom, like the case, for example, of a legged robot. So controllability and underactuation are not synonymous. We could have, even in an underactuated system, as we saw, some controllability. We cannot follow arbitrary trajectories, but this doesn't imply that we cannot arrive at some states in the state space in using different strategies. For example, using the contact forces, and we see that a legged robot is doing exactly that. It's driving his underactuated mass, which is the trunk, by the action of contact forces. So if we want to see the dynamics of an underactuated robot, we have nothing else than a term S, which is a selection matrix, appearing here. And this selection matrix, so first we see here that the number of joint is Rn, and the number of torque input is actuation input is Rm, and we can, in an underactuated robot, reorganize the joint coordinates as actuated ones that are relative to the torque input, and underactuated one that are passive. These are passive joint, Rn minus m, and the QA are the actuated ones, and are Rm. And the selection matrix, it maps the control input to the generalized forces. So you have a zero matrix that is n minus m times n, and you have an I matrix, which is n times n, identity matrix. Sorry, m times m. And therefore, the system dynamics can be partitioned into its underactuated part and its actuated part, where this is the underactuated part in red. We see that we have passive joints, so no input torque for these joints, tau equal to 0, and you have the actuated part here. As example of underactuation, we have, in addition to the Pendobot and Acrobot we already saw, the floating base robots, or better say the mobile robots. And the mobile robots extend the capability of fixed base robots, the industrial ones, because they are they allow to have move freely in a large unstructured and dynamic environment. Because the industrial robots are very accurate and good in structure, limited and non-static workspace, but they cannot move around. So with floating-based robot, we have more applications, like whenever we want to do exploration or inspection of plants, search and rescue, transportation of loads, demining, nuclear decommissioning, and in general monitoring and doing surveillance. And recently they have also some application at the agricultural level, because with legged robots we can go in the field, grasp fruits and select, put herbicides selectively, recognize whenever there is some specific action to be taken. And this is something, a very, very promising application, especially in Europe. There are many fundings on this. Examples of other underactuated robots. So think about could be, for example, an underwater ROV for inspection. You think in this case the floating base is just the rover itself, and it will have propellers that are moving it. A space robot, which is floating in space, again with propellers, can move around and it can have joints. The quadrotors, the drones, are also floating-based robots for the same reason of the underwater robot. Wheel robots that have a floating base, but this time instead of propellers or like in the case of drones or underwater robots, we have wheels, tracks, and finally legged robots that will have legs instead of wheels. But all these robots, they share the same concept, and in general, that the floating base, the trunk, for example, or the chassis is underactuated. In this case, you can distinguish between the N internal joint that are driven by the N actuators. Sorry, this is confusing. I call it M before, but yeah, now we change the notation. So if the robot is not bolted to the ground, the degrees of freedom of the system include both the internal joint, for example, the leg joint, and also the 6 degrees of freedom that represent the position and the orientation of the floating base of the trunk of the robot in space. And to the trunk will be attached all the legs, for example. That will be like fixed base manipulator. So the floating base and the joint space coordinate will have the floating base part QB and the joint space part QJ. And the floating base part can have a dimension that will be 3-dimensional for the position, for example, of the floating base, and according to which orientation representation we select, the rotation matrix or quaternions, will have a different size for this QB. And while the joint will be always Rn. And the same thing for a humanoid. We, again, in this situation, we will describe the base, the floating base, as the pelvis in general. And from the pelvis, you have attached all the links and joints related to the leg and the arms, and also the neck, depending if you have a head that is moving. Okay, so the specific case of legged robots are peculiar types of floating base robot, wherever we have single kinematic chain structures, like the legs, that branch out from the base. We don't have any kinematic loop, so nothing like this. And differently from legged robots, from fixed base robots, legged robots can fall, and the base can be controlled through the action of the contact forces. Therefore, the legged locomotion problem is only about creating the right amount of contact forces on the ground to keep balance and move the body in the desired direction. Okay, so if we write the dynamic equation for a legged robot or a floating base system, we can again partition it, and we see that before, in the case of an acrobot, we have had just this part with the passive joints, but here we have the presence of the contact forces that will appear in the actuated part of the dynamics and also in the underactuated part of the dynamics. So the first fact is that the joint torques only affect apart from this little coupling, inertial coupling, they will affect only the joint coordinates, direct influence on the actuated joint coordinates. But the floating base, which is this, can be controlled through the action of the contact forces. However, the contact forces are limited by physical law. You remember the friction cone that limits the direction of a contact force, the unilaterality, which is the ground can only push and not pull. And also the joint torques can be limited because we have actuation limits. And this means that because of this limitation on our possibility to control this robot, we have a limitation in the ability to control the displacement of the base of the robot. That's why robots can fall, can slip, have slippage, and so on. And the final fact is that the first row coincides with the Newton-Euler equation of the robot as a single rigid body. So you remember, you can think about the robot welded with all joints welded in a fixed configuration, compute inertia tensor, compute the center of mass, and then the first 6 rows of this underactuated dynamics for a legged robot are the Newton-Euler equation. This is a very good result. And the final fact is that if you supply a certain amount of torque, as we saw, the environment reacts by producing a contact force. And this contact force acts on the underactuated dynamics of the system, on the robot base, enabling the robot to move around the environment. So the locomotion problem can be split into 2 consecutive stages. The first one is to find the trajectories of contact forces that will drive our the trunk of our robot in the same direction that will correspond to some direct trajectory of the center of mass. And using the actuated dynamics, having this pattern of contact forces, we can get the, in hypothesis of no sliding contact, we can get the torque, the required joint torque to achieve the center of mass displacement that we want. And this is the end of this part on the dynamics. We will start next lecture with Octavio, that will be with you for the next 2 weeks. And the final week, I will conclude the course with the labs and with the with whatever remains from Octavio. I think it will be the controlling the Cartesian space, and with the final labs where we put everything together, whatever we learned. We'll see the control in the joint space, in the Cartesian space, in contact with environment. We will put all the ingredients, the forward oil integration, all whatever we saw will be in the lab, in the Python lab, and you will have an understanding of a practical understanding of everything. So unless you don't have any question, see you next week. Next week I will be online, of course. Octavio will come here. And have a good evening.